So let's get started off. So we've been discussing the various ideas and concepts within the recovery subsystem of the relational database management. So the principal tool that we use is log, and log is a sequential file where we keep making entries about the transactions that are under progress, and we keep certain important information recorded in the log, and we use that log to recover from failures. So in that context, we have looked at what are the various log entries, and then we started looking at various specific logging methods, and we looked at what is called an undo logging. In this lecture, we will focus on other logging methods, particularly what is called redo logging and also undo redo logging. We will see that. So in undo logging, as we have seen in the last lecture, it basically cancels the effect of incomplete transactions. So it keeps track of the old values of the items that the transactions in progress have changed in the log entries, and making use of these old entries, it will cancel the effect of incomplete transactions. And because of the way it has been made, we don't need to specifically do anything about committed transactions. Now, but one major issue with this particular way of logging is that the database items, all the database items that the transactions have changed, a particular transaction has changed, have to be written in an urgent manner to the disk before we allow the transaction to commit, right? So this is what is called force writing, and so we don't have much flexibility in the matter. So suppose there is a block that has been actually is probably useful for many transactions, and they are going to be changing that. So we will not be able to kind of accumulate the changes made by several transactions and then write this block at a time. We will not be able to do that. So whatever be the changes that were there right now, when this particular transaction which has made use of this block wants to commit, then we have to send that block back to the disk. Only then we can make a commit. So this kind of results in a lot of I/O. So is there any other? So before we proceed to undo redo logging, let's look at the in some sense the the inverse of this kind of method called the redo logging, where we ignore the incomplete transactions and then we repeat the work of committed transactions. So obviously, if you have to repeat the work of your committed transactions, the log entries that we have to make use of now have to be different. So in the log entries now, we will keep track of the new value. Whatever the transaction is changing, some database item if it changes, we will keep track of the new value. So the update log, all the other log entries will remain as they are. The update log entry will now become transaction ID, what is the item, and what is the new value. What is the new value? And we will see how exactly as the method proceeds. So the redo logging method is simple. So before, this is also called write ahead logging. So before we write anything onto the database, we must ensure that all the log entries made by that particular transaction are all on the disk and including the committee entry. So read it like this. So before modifying any database item X on the disk, it is necessary that all log records pertaining to this modification, including the update records as well as the committee record, must reach the disk, must appear in the disk. So the actual update of the items on the disk can proceed in a leisurely manner afterwards, but as soon as possible. Okay. So we have that flexibility now. So this particular principle is what is called write ahead logging rule. So the items will flow like this. First, the update log records will go to the disk, and then the commit entry will go to the disk, and then actual changes to the database on the disk will be carried out in a little leisurely manner. So, this will not, there is no particular hurry to write all the items to the disk. The transaction is not, kind of waiting to commit. So, it does the commit entry. So, we allow it to go. The main reason why we can get away with that is that we have a record of what are the changes that particular transaction has done in the form of the update records. We have the new values. And so, in case the transaction itself fails to do the updating of the database, we will be able to do that with the help of the log records. So, that is the idea in this. So, let us go back to this redo example of 100 rupees being changed, transferred from account A to account B, the same example. So, you are familiar with all these columns now. So, we are using a single variable and the actual method is same. So, we read A into M, reduce it by 100, write it, read B into M, increase it by 100 and write it. Okay. Now, the only thing here is that we do a commit T and okay. So, let us focus on the log now. The log records will now keep the new values. Log records will keep the new values. So, when write AM has occurred, what we are keeping track now is the transaction T has changed this DB item A and the new value is 400. So, that is what the log entry will have. And then transaction in a similar way, transaction B has changed transaction has changed the item B and its new value is 69. So, these are the log entries, and as soon as we do our work, as soon as the transaction completes its work, it will make a commit T entry. So, that means it will request for a commit and it will actually be internally there will be a flush log and so all these entries will be permanently there on the log file, including the commit T. Then the transaction is deemed to be committed. Now, in a leisurely manner, okay, there may be some other interleaved operations here of other transactions, but at some point of time we will do an output A, output B, where we will send these items A to the disk. Now, let us also again look at the various failure scenarios and then see how exactly we will recover from this. So, the recovery method is like this. We will examine. So, if a crash occurs, the recovery module is the first one that gets control of the system. So, it will open the log file and then figure it out as to what is there in the log and then examine the log, partition the transactions into two sets, committed set and the incomplete set. So, the committed set is the one, these transactions for which the commit T exists. Commit T exists on the log. For the incomplete transactions, either abort T exists or commit T does not exist. So, we will partition this like that. And now, we will, since we are redoing the work of transactions, we are writing new values. So, we will have to start from the beginning of the log and then start doing the work of restoring the state of the database. So, we will examine the log in the forward direction. Remember, this was in the reverse direction in the case of undo logging. So, for every update record that we find, the transaction T has changed database item and V is the new value. So, if T is incomplete, then we are not going to do anything about that transaction. That is because if the commit T record has not reached the disk and so we are able to classify it as a committed thing, the transaction would not have attempted to do any changes to the database anyway. And so, if it is an incomplete transaction, we will do nothing. If it is a commit transaction, committed set, if T is committed, that means not committed, it is there actually in the commit set, that means its commit T record exists in the log. Okay. So, then we are kind of unsure if all the effects of this particular transaction have actually reached the disk or not. But fortunately, because of this write ahead logging principle that we have as part of the redo logging method, we have all these log entries which record the new values already on the disk. So, we will make use of those log entries and then redo all the changes as per the log entries starting from the beginning. Okay. And so, for every, of course, after you do this, we will do and we will make an about T log entry for the incomplete transactions and then do a flush log, so that on this record that we have looked at transaction T and notice that it is an about a transaction is actually available in the log. Okay. And then of course, we will have to resubmit some of these incomplete transactions. We have to do resubmit, ensure that they get done. Okay. So again, in this example, let's look at the various cases. A crash occurs before step 8, that means before commit T. So if crash occurs somewhere here, then obviously T is an incomplete transaction. It has not made a commit T yet. So no action is actually required, and we basically resubmit this transaction. Okay. Now let me change slide. So crash occurs after the step 8. After the step 8, somewhere here the crash occurs. So again, there will be two cases here. So whether the commit T record itself has reached the disk or not. So that will basically decide the fate of the transaction. If the commit T record has reached the disk, then we will deem it as committed and then we will redo the work. So if the commit, remember one thing, that if commit T has reached the disk, all these previous entries would have also reached the disk, because the log is always written in a sequential manner. You don't write only this entry into the log, you always write all the previous items on the log. So the moment this is there, we know that all these are also there, and so we can actually redo the work of this particular transaction. Okay. So there are two cases we will consider here. The commit T record has actually reached the disk, and so we will classify T as a committed transaction, completed transaction, and with the help of these log entries, we will redo the work of that particular transaction. And the other case where the crash occurred, but then the flush log itself, even before the flush log itself, the crash occurred. So the commit T actually has not reached the disk. So this is a little unfortunate situation, because this fellow has actually in fact finished all the work and but unable to manage to get this commit T into the disk. So, but we don't know the situation, what exactly has happened, we will not know. So what we will do, our uniform policy here is that we will not take the risk. We will say that let this particular transaction run again. Because we really don't know when exactly the crash occurred. So the DB disk is T is treated as incomplete and no action is required, and we will actually resubmit it. Okay, is that clear? Because see, if commit T has not reached the disk, then we are very sure that yeah, see, the issue of commit T reaching the disk has to be carefully examined. So if the thing has reached the disk, then maybe actually you have kind of system has agreed that the transaction has committed, and so we are under obligation to redo its work. But if commit T has not reached the disk, then we are actually not, the system is not obliged to do any changes, and we are also not sure what exactly has happened, and because some of these log entries might themselves not be available, we don't know. Whether we have the complete set of log entries or not, we don't know if commit T has not reached this. And so we can't really take any risk, and we'll say that okay, redo this transaction, resubmit this transaction. So that is the policy of redo logging. Of course, if the only crash occurs after step 9, then we are very sure commit T is surely has reached the disk, and so we will simply redo all the work, because we have already committed that it is done. So we have to do, the system is under obligation to do the work of the transaction. In this case, we actually will ignore whether it has succeeded to do one output or other output or both of them or something like that. We will simply ignore all those possibilities, because this writing of the new values onto the again new values or old values, okay, it does not matter if you do it again. So we will do some additional work which might involve rewriting the same values, but it is safer, right. So we will do it. So that is what the redo logging method is. So let us now compare these two things. So the undo logging cancels the effect of incomplete transactions, and all the DB items are sent to the disk before the transaction can commit, and it results in a lot of IO, and IO cannot actually be bunched. Bunched means actually I can't wait for several transactions to do certain changes to a block before I actually shift it to the disk. I have to on an urgent manner shift the block to the disk whenever a transaction that has touched that block commits. In the redo logging, that stress is not there, but then only thing is that since we are relaxed about when to shift the blocks of the blocks to the disk, it is possible that lots of these blocks are hanging around in the memory. Okay, and so the buffer utilization actually might come down. So when you actually want to bring in a new block from the disk to the buffer, we suddenly find that there may be space there, because all these blocks which have been touched by this running transactions which are committed have to be there in the memory before, because we know that we are going to write them to the disk at some point. Okay, so there is another interesting method, which combines these kind of principles. So this is called undo redo logging, where it provides better flexibility, but the expense is that we have to do a bit more detailed logging, where we actually have to keep track of both the old values as well as the new values. So in the undo redo logging, the update entry will be actually the transaction ID, the DB item X, what's its old value and what's new value. So that way we have the flexibility. In case we have to roll back a transaction, we know the old values. If we want to redo the transaction, we know the new values. So that way we have greater flexibility, and so the only principle that we have to follow, of course, is that these log entries are very important. Before we do any changes to the database on the disk, ensure the log entries reach the disk. So before modifying any DB item X on the disk because of changes made by some transaction T, it is necessary that the update record TXUV appears on the disk. And the commit and disk changes actually can happen in any order. Of course, commit will happen only after all the operations of a particular transaction has been actually completed, and the disk changes can be actually interspersed with commit. Okay, so let us look at this same example, where we are now adopting undo redo logging method. Okay, so look at the changes that are there in the log entries. So when write AM happens, we know that, so the log entry to be made is that transaction T has updated this item A and its old value is 500, new value is 400. Like that we make a detailed log entry. Notice that these log entries can actually be fairly big because we said what is the lockable item. The lockable item is a block. So the DB item is a block, and so there can actually be pretty big log entries. Even though here actually I am just showing the crucial values here, but the entire DB item has to be put in the log. In a similar way, when transaction writes B, we will put 1500, 1600, the old value and the new value. And now we do a flush log to ensure as soon as the transaction completes its work, we do a flush log because we now are ready to update the database with the changes, database on the disk with changes. So before we do that, we have to make sure that all these log entries have reached the disk, and so we do a flush log, and then we will actually do. So of course, it is advantageous for the transaction to kind of ensure that the commit T record reaches the disk as soon as possible. But it's kind of left to the scheduler to actually look at this possibility. Okay, so it might actually change. It might actually transfer some disk block to the memory, even though to the memory block to the disk, even though the transaction itself has not made the commit T, because it knows that if it is necessary, I can undo the transaction. Okay. So again, the principal recovery method is like this. Again, we are going to after the system wakes up, we will again examine the log and partition the transactions as usual, as we have done earlier. So everything depends whether the commit T exists in the log or not. And the recovery method is redo all the committed transactions in the order earliest first in the log. So for every transaction, we can actually look at all its operations in either direction. We can look because we have the entire log with us. So for the committed transactions, we do a redo step in the forward direction, and for all incomplete transactions, we will do a undo in the latest first, and it's of course necessary to do both of them. So let's look at. Are there any questions now? Let's look at this. The various scenarios. The only thing, of course, is so the crucial thing is this commit T there on the disk or not? That's the crucial thing as far as this thing the method is concerned. So if the crash occurs before commit T is on the disk, that means somewhere here, if the crash occurs, then we are going to deem the transaction T as incomplete, and it will be undone, even though it has actually completed its work and transferring some of the changes to the disk. So it has done an output A. Okay. So some changes have actually reached the disk. But then we know that the transaction T is incomplete, and since we have the old values with us, we will do an undo. We will do an undo and restore the old values. But suppose the crash occurs and then the commit T record is actually on the disk. So then we treat this as completed transaction. Again, notice one thing, this is not just with respect to this particular transaction. Remember that transaction operations of several transactions are getting interleaved, and they will actually be happening in an interleaved fashion as per some transaction schedule, which is following the two-phase locking protocol. So, we have to combine these two things. We are right now talking from terms of only error recovery, but we have already discussed the issues with respect to complex serializability. So, complex serializable schedules are actually happening in the system, because all the transactions are following two-phase locking protocol, and so interleaving is happening. So, this, though I am showing only the operations of one particular transaction, in reality there are actually operations of several transactions interleaved. And so, there are a bunch of these transactions which are incomplete, and a bunch of them which are completed, and so we have to actually do a redo and as well as undo operations. Okay, so let's come to another interesting issue now. Look at this scenario. This brings it actually a absolutely new kind of requirement into the picture. So, let's look at this again, revisit the issue of this dirty data and commits. Okay. So, so suppose look at this scenario, consider some transactions T and S. So, T has modified a DB item X and it is doing some more work. So, it has kind of released the lock on item X. It has released. So, it does not require any more items to be locked. So, following the two-phase locking principle, it has released the lock on DB item X. So, it was available for somebody else. So, meanwhile, S has read and completed its work. Okay. Now, the order among commits we have not actually discussed anywhere. Suppose S is allowed to commit. Suppose S is allowed to commit. This is the classic case of the dirty data problem. Suppose now S is allowed to commit by our transaction system, and after that the T which has released the lock on X and proceeding with some work has found out that it does not read any more items to be read, but it has found some internal error and basically decided to abort. It has decided to abort. Now, S has read dirty data, right. So, it has read some incomplete, it has read some value that is not supposed to be there, because this change that was done by S on this item X is now going to be rolled back. It will be undone. It will be undone because the transaction itself requested for a abort. So, in case either when a crash occurs or actually when aborts happen, the system is obliged to run this failure recovery methods even for transaction abort requests, not only for crashes. So, when a transaction abort request comes, then it will take this policy of failure recovery and then actually try to undo the operations of that particular transaction. For that particular transaction, it will do an undo, rollback. It will do a rollback. But then we have allowed S to go ahead and commit. So, this should never be allowed actually in the case, because this basically goes against the principle of what is called committing at all, right. So, if you allowed it to commit, then we are giving a commitment saying that all the work that is actually done by S is is valid, and we are going to keep a permanent record of that. But unfortunately, yes, the transaction has read some dirty data and it's actually made some mistakes, and we can't do an undo of S, because the very meaning of commit is that we are giving a commitment saying that all its changes are going to be permanently recorded. So, we can't roll back that particular transaction. Okay. So, remember, look at the sequence. Right? So, the T has modified item and is actually still running. S has read this item that was changed by T and requested for a commit, and the system allowed it, and later the transaction T has some internal error and requested for an abort, and the system allowed it. If this happens, if this sequence of things happen, then we are actually contradicting ourselves, because we will not, our meaning of commit itself is not proper. So, because see, the ideal thing for us to do is that if T has requested for a rollback, okay, so we should have probably made note saying that this particular transaction S has read some item that has been changed by T, make a note of that, and roll back that also. If T is getting rolled back, okay, we should make a note somewhere that S has read some item that has been changed by T, and so we should roll back that also. We should stop it and roll it back. Like that, man, there is some problem with your transaction, you cannot proceed, we have to undo. So, that is a proper way of handling this kind of situation. So, even though we did not discuss these this kind of interactions so far, so right now we are able to see that if this kind of issue of dirty data arises, then we really have to be careful, and we cannot independently treat these commits and aborts of transactions in an independent manner. So, the DB will get into trouble. So, this particular issue is what is called recoverability. We have lost the ability of recovering it itself. So, there is a very fundamental requirement. Okay. So, this issue has been termed as what is called recoverability, recoverable schedules. So, let me introduce. So, serializable schedules we have introduced earlier. Now, let us introduce recoverable schedules. Recoverable schedules are those schedules in which the transaction T commits. So, no transaction T in the schedule commits until all the transactions that have written an item that this particular transaction has read have committed. Okay. So, if I am reading, if I am a transaction and I have read an item that has been released by some running transaction, active transaction, which has not yet committed, then I should not go and commit, because I do not know what is there that other fellow's position is, whether he will decide to commit or whether he decides to abort, I really do not know. So, if I am an active transaction, okay, if I am an active transaction, I am doing my work, okay, I have acquired the logs that are released by other people and done the work, but then I should know, of course, there may be no particular way of whether I knowing it, but let us see how that can be handled. But basically, I should be aware that some transaction might have actually changed the item which I have read, and so that transaction, whether it completes or not, I do not know at this point of time. So, if I request for a commit and actually the system grants that commit, then we are in trouble. And so, what the system has to do is to keep a watch now of all these running transactions and then ensure that this kind of a principle is enforced, that if transactions request for commits, we should ensure that whatever the transaction item that it has read from other transactions, we should watch that, and unless those transactions commit, we should not allow this fellow to go ahead and commit. Right? Is that clear? For an active transaction, we must somehow make a note as to what are the items it has read from other running transactions, and we must wait for those other transactions to either commit or abort, whatever it is. If all of them commit, then I can allow this particular transaction to commit, and if one of them aborts, I should abort this fellow also, because he has read some item which has been changed by somebody and that fellow is aborted, so I should abort this fellow also. Okay. So, T needs to wait till each of the transaction from which it has read completes. If all of them commit, then I can go ahead and commit. If one of them does not commit and aborts, then this transaction T also has to abort. So, in such situations, what are called cascading aborts work happen. Cascading aborts, we call them cascading aborts or cascading rollback. So, because the rollback of one transaction, some other transaction will have to be rolled back, and because this transaction is getting rolled back, maybe some other transaction has read some item that has been changed by this fellow, that fellow also has to be rolled back, and everybody has to be, a sequence of transactions may have to be rolled back. That is called a cascading rollback. But recoverability is really an essential feature, because to give proper meaning to commit and aborts, recoverability is an essential requirement. So, this kind of combines both these issues of interleaving and then the order among commits exactly. So, this is one basic requirement for schedules to satisfy, and it turns out that these two things, the serializability requirement and the recoverability requirement, these happen to be orthogonal actually. We can see that they are, so that means it is possible that for some schedule is actually serializable but not recoverable, whereas it is recoverable but not serializable. Basically that you can see, because we do not, so recoverability versus serializability, these are turning out to be orthogonal concepts. So, it is possible that a recoverable schedule is not conflict serializable, because recoverability actually does not put any restrictions on locking two-phase right now. We do not, all that we are saying is this: who has read from what item, and then commit should be in a particular order. So, it is bothered about commits. Whereas serializable schedules may not be recoverable, because serializability definition, we can see that it only bothers about what are the conflicting pairs of operations, and are they same in the same order as any other or some serial schedule. That is what serializability definition requires. So, it does not put any restrictions about committing. Okay. So, these two happen to be orthogonal concepts, but we in fact we want both of them to be satisfied for practical for operationally correct schedules. So, a schedule has to be both conflict serializable as well as recoverable for us to be useful, for us for it to be useful for us. Okay. So, we will see how exactly we can achieve this in the next class. Actually, I think we made considerable progress. So, the next class will be, I think, pretty short.